So, we begin a new chapter today on oblique shock waves. So, we will start this chapter with a recap of what we learnt about normal shock waves, and then we will see how an oblique shock wave differs from a normal shock wave. Okay. So, the applications and other uses of oblique shock waves and where they occur and so on, we will discuss afterwards. So, if you recall, we started our discussion on normal shock wave by considering a situation like this, where a normal shock propagated with a velocity Vs into a quiescent medium. And this was in a frame of reference where the observer is stationary. So, observer and as a result of passage of the shock wave. So, the shock wave is propagating like this, and as a result of passage of the shock wave, the fluid in this section attains a certain velocity. There is a pressure, increase in temperature and so on, but the fluid ahead of this is quiescent without any velocity. So, this was the scenario that we were looking at, and then we changed the frame of reference. We said that we will get into a frame of reference where the observer moves along with the shock wave. Right. So, he moves along with the shock wave. Then we drew this kind of a sketch where now the shock wave appears stationary. As the observer is moving along with the shock wave, the flow seems to approach with a certain velocity and recede with a certain other velocity. Right. So, the velocity with which the flow approaches the shock wave is, we label that as u1, which is actually equal to the shock speed. So, this was labeled as 1 and this was labeled as 2, and so state 2 here, the flow recedes with a certain velocity u2, and we saw that, or we showed that u2 is less than u1, that is the permitted solution, and the process is a compression process. An expansion shock wave was forbidden by second law of thermodynamics. So, these are the highlights of our discussion on normal shock wave. Notice that the velocity vector both before and after in this frame of reference where the observer moves. In this frame of reference, notice that the velocity both before and after is normal to the shock wave, and hence the name normal shock wave, and there is no change in the direction of the fluid after it passes through the shock wave. Right? These are the highlights of the normal shock wave compression process. Oblique shock wave, we start with the same scenario. Okay? We start with the same scenario. The only difference is so let me draw this here for the oblique shock wave. And let us label this as 1 just like before, label this as 2. So, this is in a frame of reference where the observer is stationary. Now, let us say that the observer now gets onto a frame where not only does the observer move along with the shock wave, the observer also moves along the shock wave. Please notice the difference. Here the observer moves along with the shock wave. Here the observer moves along with the shock wave and along the shock wave, meaning the observer also, let us say, travels this way with a certain speed which I am going to label as v sub t. The observer can go this way or that way, both are equivalent, that is not an issue. Right? So, the observer now moves along the shock wave in addition to moving along with the shock wave. Okay. Now, so when we go to this frame of reference where the observer is moving in this manner, now I see that the velocity of the fluid that is approaching me has two components, one component in one direction, another one which is normal to this. So, let me draw the shock wave. So, because the observer is moving this way, the flow seems to approach the observer in this direction with the velocity which is equal to this velocity, correct. So this is the tangential component of the velocity, which I can label like this. Now, because the observer is also moving this way, the flow seems to approach with the velocity in the normal direction with the value equal to Vs, just like what we saw here, correct. That is the normal component. So, I am going to show the normal component like this. So, I am going to use the subscript n, here I use the subscript t to denote tangential component, here I am going to use subscript n to denote normal component. This normal component is equal to Vs, right. The observer has two components of motion, one which is along the shock wave, so the fluid acquires that in the opposite direction, one along with the shock wave or normal to the shock wave, so the fluid acquires that velocity the opposite direction. This is quiescent medium, so it looks like this. So the resultant velocity vector in this case is going to be like this. So this is u1, this is vector u1. Notice that u1 is not normal to the shock wave. Here u1 is normal to the shock wave, here u1 is not normal to the shock wave. Now what happens to the flow after the passage of the shock wave? That is state 2 and that is state 2. Now there is no shear force or any other force acting in the tangential direction to the shock wave. So the tangential component of the velocity will remain the same across the shock wave, there is no change, right. Only the normal component of velocity is reduced as a result of compression across the shock wave. So normal component reduces, tangential component remains the same, okay. So that means if this is my tangential component which remains the same, my normal component is less than what it was before, let us say something like this. So let us call this un2, this is normal to the shock wave. So now the resultant vector, this is u2. Is that clear? Tangential velocity vector or tangential component remains the same, normal component alone decreases, just like it decreased in going from here to here. In fact, the reduction is actually the same. If you consider only the normal component, it is as if it is going through a normal shock wave. Whatever we have developed here, the theory is applicable here also. Only thing is we have to now worry about directions, okay. This direction. So now another thing that we must keep in mind is when the observer starts moving along the shock wave this way, the shock wave also appears to slide upwards, right. So the shock wave now appear, that acquires a direction. So the shock wave goes like this, because the observer is moving along the shock wave like this, the shock wave seems to slide above the observer. So that means the shock wave has a direction now, in contrast to what we had before. There was no directionality to the shock wave before, now there is a directionality to the shock wave in this frame of reference. Remember, this is the observer moving frame of reference. Okay. This angle is usually denoted as beta or the wave angle. That is the angle that the shock wave, this vector makes with the vector u1, the acute angle between the shock wave vector and this vector u1. I will show this in a slightly different orientation so that you become more comfortable, but this is the picture that you will see if you go from this frame of reference to this frame of reference. Now we want to find out one more thing, is the flow deflected or not, is the other thing that we want to see. Here there was no change in the flow direction, flow was not deflected at all. Here we wish to see if it is deflected or not and by how much. We can easily see that the velocity vectors are not parallel to each other, obviously, because u and 2 is smaller. So which way is the flow deflected? Towards the shock wave or away from the shock wave? If you take this length and put it here, right, this will come up to, let's say, somewhere up to there. This would be un1. If I superimpose this on this, this would be approximately un1. Then the resultant velocity vector would look like this. So that means the flow upon passing through the shock wave is deflected towards the shock wave by a certain angle. That angle is called the flow deflection angle. Okay, that is called the flow deflection angle. This angle is called the wave angle. I am going to make this more clear in a minute. Now the important point here is this angle is measured with respect to u1 and the direction of the shock wave. That is why it is called the wave angle or the shock angle. Now life becomes easy if I rotate this figure. If I rotate this figure so that u1 becomes horizontal, then things are a little bit clearer to see. Okay? So notice that this is the true picture. For our convenience and ease of use, we are going to rotate this through an angle beta, so that this becomes horizontal, so the flow deflection becomes easy to see. Flow deflection is not so easy to see in this diagram. So I am going to rotate this diagram this way, counterclockwise, by an angle beta, right. So if I rotate this, in the counterclockwise direction, when I do that, my shock wave rotates through an angle like this, right. This is the direction and this angle is, what is this angle? Beta, because I have rotated through beta. So this angle is beta, and so this is my u1 which has become horizontal now, this is my ut and this is my un1, okay. So I have rotated this. This is not a new reference frame, it is the same reference frame, but instead of looking at this figure like this, if you will, I am looking at the figure like this, so that u1 is horizontal, okay. You must understand that it is not a new reference frame, it is the same reference frame. Okay, I am tilting my head so that u1 becomes horizontal, right. So that is what has happened here. So this is u1, this is beta, this angle is beta, and again notice that this angle is also beta. Now when I draw the diagram on this side, again this is ut, I am sorry, un2 is slightly draw it like this. This is un2, this is ut, this is u2, okay. Notice that ut remains the same, right. un2 is less than un1, and now you can see that this was the original velocity vector direction. What is this angle? That is the flow deflection angle, usually denoted by theta. So this is the flow deflection angle theta. So let us write it down explicitly. Theta is the flow deflection angle. And beta is the wave angle. Notice that both these angles are measured with respect to u1. Please bear this in mind. Just because we have drawn this horizontally does not mean that these angles are measured from the horizontal. Both the angles are measured with respect to u1. So, the flow deflection angle is the angle through which the flow is turned with respect to vector u1, and wave angle is the angle that the vector along the wave makes with u1, not the horizontal. This is only for ease of illustration, nothing more than that. Okay. So, let us write down a few ideas from these two, and then we will go from here. Okay. Notice that insofar as the normal component is concerned, the oblique shock wave and the normal shock wave are the same. Okay. So, as far as normal components are concerned, they are both the same. The oblique shock wave and the normal shock wave are identical. Why is this important? Because if I have a flow that is approaching a shock wave like this with, let us say, static pressure P1, static temperature T1 and velocity u1 with a normal component equal to this, how do I get the static pressure and static temperature after the passage of the shock? I use the normal shock table, but instead of using m1, when I go to the normal shock table, I use this Mach number. mn1 is what I use when I go there. Remember, static quantities are frame independent, right. So, the static pressure and static temperature that I calculate using the normal shock relationship for this will be the same as for this frame of reference also. Stagnation pressures will not be the same, static pressures will be the same. So, that is why this is very important. So, static quantities across the oblique shock waves can be calculated using the normal velocity component, just like you would do for normal shock wave. Okay. Next, flow is deflected after passage through the shock wave. In fact, which way is the flow deflected? The flow is deflected towards the wave, right. The flow is deflected towards the wave. Or equivalently, there is another terminology that is usually used, the flow is turned into itself is what people use, although that is very confusing. I prefer this because this has a direction. So, you can easily see whether the vector is shifting towards this direction or moving away from this direction. So, I do not like this other terminology, but that is also used. Flow is turned into itself. This is a little bit confusing because when you look at some complicated situations, you really do not know which is turning into itself and which is turning away from itself. Whereas this one, irrespective of the orientation, once you draw the sketch the directions, it is always clear whether what you are drawing is a shock wave or not. Because later on we are going to look at expansion waves also, not the counterparts of this, but infinitesimally strong expansion waves which will actually deflect the flow away from itself. Okay, so, it can be confusing. So, towards the wave is a much better way to describe the flow deflection. Okay. Next, probably most important point, let us say that we consider a situation where we have something like this and something like this, and let us further state that u1 is the same in both cases. P1 is the same, T1 is the same. That means m1 there and m1 here are the same. However, mn1 is always going to be less than m1, right. So, the loss of stagnation pressure across this shock wave is going to be less than the loss of stagnation pressure across this shock wave for the same Mach number, because the normal component is always less. Okay. Since the normal component of the velocity less than the magnitude of the velocity itself, loss of stagnation pressure is less. In an oblique shock wave. Why is this important? This is important because in practical devices, we saw that beyond a Mach number of 2, the loss of stagnation pressure in a normal shock wave was 70%, as much as 70% or so. So, it is actually not possible or very impractical to compress flows at high Mach number using a normal shock wave. So, the strategy in practical devices is to exploit this fact, compress them through a series of oblique shock waves, and once the Mach number gets below 2, terminate with a normal shock wave. That is very effective, very efficient. Not efficient, but very effective. Remember, we said normal shock is effective but not efficient. So, utilize the best aspect. Decelerate the flow from a Mach number of, let us say, 4 or 5 to maybe 2 using a series of oblique shock waves which has a lesser loss of stagnation pressure, and then terminate with a normal shock wave. So, oblique shock waves find a lot of use only because, mainly because of this reason. Otherwise, everything is similar to this. Pressure rises across the normal shock, the oblique shock wave, temperature increases, and the velocity, normal component of velocity decreases. The tangential component of velocity remains the same. Okay. Now, because the normal component of velocity alone decreases and not the tangential component, across an oblique shock wave, the flow becomes subsonic only with respect to the normal component, not the total velocity component. Mn1 is supersonic, Mn2 is always subsonic because there is a normal shock wave. However, M1 is supersonic and M2 can also be supersonic. Most of the situations M2 is also supersonic. Okay? That is the next important point which we will write down here. Mn1 greater than 1, Mn2 less than 1 always. M1 greater than 1, M2 greater than 1 most of the time. We will see when this is not satisfied. So, where are normal shocks used? As I said, normal shocks are very, where are oblique shocks used? Oblique shocks are very effective for decelerating and compressing a supersonic flow. So, they are used in diffusers and also turbomachinery blade passages. If you have a transonic stage where the stage handles mixed flows, then it is used in transonic stages also. For example, transonic compressor stages. So, in these applications, you design the geometry so that you generate shock waves of a certain angle and strength. So, this is controlled. You control the angle, shock wave angle and the flow deflection and the strength of the shock wave in these applications. There are other applications where you do not really control this, and that is what we saw when we discussed nozzle flows, over expanded nozzles. When it comes outside, there is a shock wave, that is oblique shock wave, that is generated which compresses the flow, right. So, there the strength is determined by the back pressure and the nozzle geometry, right? So, this appears also in over expanded nozzles. So, here we do not really control the the angle. It is determined by other fluid dynamic parameters. Here the geometry is designed to generate or trigger an oblique shock at a certain angle to accomplish a certain amount of flow deflection. Okay? We are going to see the dynamics of this. Basically what we want to do is just like what we did for the normal shock wave. Given M1, we were able to find everything else. The pressure rise across the shock wave, M2, temperature rise, P02 over P01. We are going to do the same thing here. But here there is one additional quantity. What is that? The two additional quantities. That is the wave angle and the flow deflection angle. So given M1, theta and beta, how are we going to determine, how do we determine the downstream Mach number and all other flow properties? That is our next task. So how do you actually trigger an oblique shock in a practical application? And we said that in some cases we design so that we trigger an oblique shock at a certain angle. Let us consider the following situation. Let us say that we have supersonic flow which is flowing along a surface like this, and it encounters a corner like this. So let us say that the corner is inclined at an angle theta to the horizontal. So when a supersonic flow encounters a corner like this, the flow has to be deflected through an angle theta, or it has to be turned into itself. So what happens is, so something is generated from this corner, right? And in this case, you know that after passage through the wave, let us say that this is some wave. We do not know whether it is an expansion process or a compression process. But we do know that after passing through the wave, the flow is deflected towards the wave, right? You can see that it is deflected towards the wave through an angle theta. Remember, the wave direction itself is like this. So a wave is generated from the corner, it goes like this, right? So the flow is deflected towards the wave, so that means that this is an oblique shock wave. So this is how we trigger an oblique shock wave of a certain strength and angle. So this is the deflection angle, this angle is the wave angle beta. So if I design this theta, then for a given Mach number I fix the theta, I get a wave of a certain strength and the properties are also of a certain value. So I trigger a series of shocks like this, I can successively decelerate the flow and bring it to a value that I want. That is how we trigger oblique shock waves in practical applications. So the corner is designed to generate an oblique shock wave which deflects the flow through this angle and a wave angle beta. Notice that the opposite version, where we have an expansion fan which deflects the flow through an angle theta away from itself, is forbidden. Okay? So the oblique shock is a compressive wave which deflects the flow towards the wave by a finite angle theta. Now the counterpart to this, where a wave deflects the flow away from itself through a finite angle theta, which would be an expansion process, is not allowed by second law of thermodynamics. Let us write that down also. So an expansion wave which turns the flow away from the wave through a finite angle is forbidden by the second law. The important point here is that turning through a finite angle. We will see in the next chapter that if the flow turning is through an infinitesimally small angle, then expansion waves are allowed. That is an isentropic process. Entropy can remain the same. This will actually require the entropy to decrease. That is not allowed in an adiabatic flow. If the flow turning is through an infinitesimally small angle, then such expansion waves are allowed. Okay? So, most important point here is that what is not allowed is turning through a finite angle in an expansion corner is not allowed. Okay? So, the situation that we are talking about is the exact opposite of this. So, if we have and instead of a corner which goes like this, let us say we have a corner which goes like this. So, this is deflected, trying to deflect the flow away from itself through an angle theta, right. So, an expansion wave which can accomplish this just like this of a finite strength is not allowed. So, this is an expansion wave which deflects the flow through a finite angle. This is not allowed by second law of thermodynamics. Yes?
Sir, the value of un1, will it be always greater than
un1, yes, because as far as the normal component is concerned, we said that this is a normal shock wave. So, normal shock wave, the Mach number approaching the flow is always greater than 1.
But if u1 is very near to 1 and it's a component of...
Yeah, then it will become an acoustic wave. It will become a shock wave of infinitesimally small strength, right. It cannot be subsonic, because if it is subsonic, then we have other problems, right. That is not allowed by second law. It has to be it has to be either an expansion process. You cannot have a compression process where the flow is subsonic and it is compressed further. The shock wave always moves with supersonic speed in a quiescent medium, which is why the flow always approaches the shock wave with a supersonic Mach number. The smallest possible is an acoustic wave which moves with the speed of sound. So, there cannot be anything less than that. A wave solution, as we discussed in our earlier chapter, a wave solution is permitted only if the speed is sonic or supersonic. The nature of the governing equations is such that the equations are hyperbolic when the velocities are supersonic. So, it is only when the equations behave with a hyperbolic character that wave solutions are permitted. If the flow velocity is subsonic, then the equations behave in a manner called elliptic, and there is no wave solution for an elliptic equation. Wave solutions are permissible or permitted only for hyperbolic equations. Okay, so what we are going to do now is relate m1, beta and theta to m2 and other downstream properties. So let us write down the governing equations. They are almost the same as what we wrote down for normal shock. So we are going to write it in terms of the normal components, rho 1 un1 is equal to rho 2 un2 P1 plus rho 1 un1 square is equal to P2 plus rho 2 un2 square. Energy equation remains the same, H1 plus 1 half un1 square plus ut square is equal to H2 plus 1 half un2 square plus ut square, and ut remains the same across, we know that. So ut square cancels out. So we are left with the almost the same thing as what we had before. In addition, so this implies that T02 in the, well, we can leave this, we will pick it up later. This is fine. So this is the governing equation. And what we want to do is obtain a solution which relates m1, theta and beta to the downstream properties. Okay. Now, if you look at the velocity triangles here, you can see that this angle, we have to calculate this angle. This is 90 degrees, right? U1 and ut are perpendicular to each other. So this is 90 degrees. And this angle is beta. So that this angle is, what is this angle? Beta minus theta. Right? So I am going to write down the following equations from this velocity triangle. Un1 equal to u1 cosine beta. Un1 is u1 cosine beta, and un2 is equal to u2 sine beta minus theta. Did I do this right? Oh, sine beta, thank you. Thank you. And we also have ut is equal to u1 cosine beta, which is also equal to u2 cosine beta minus theta. So from these two, I can write this as un1 over un2 is equal to tangent beta divided by tangent of beta minus theta. Okay, there is a u1 over u2. So if I divide these two expressions, I get a u1 over u2, and I can get u1 over u2 as cosine beta minus theta divided by cosine beta. So I have eliminated that. So I end up with something like this. This is one relationship for un1 over un2. But I can also see from here that un1 over un2 is equal to rho 2 over rho 1. So I can do that also. So from the continuity equation, I can write the following. And if I use the equation of state, I can write this as P2 over P1 times T1 over T2. Now, the right hand side, remember these are static quantities, and we already wrote down relationships when we discussed normal shock waves. We already wrote down relationships for these two in terms of m1 and m2 at that time. So the m1 and m2 that we used there now become mn1 and mn2, right? That is what we are going to do. So if you rewrite this, this can be written as, if you use those relationships from normal shock wave, I can actually write this as gamma plus 1 times mn2 square, I am sorry, mn1 square divided by 2 plus gamma minus 1 times mn1 square. So, this we obtained, the right hand side we have obtained from normal shock relations after replacing the m1 and m2 there with mn1 and mn2. Okay, remember we knew mn2 also, we had eventually solved the equation. So, we know mn2, so I have written everything in terms of mn1. But we also know that mn1 from these velocity triangles, or if you look at this relationship, divide both sides by square root of gamma r t1, what do I get? I get mn1 here, right? I get m1 here. So, mn1 is equal to m1 sin beta. So, it is the same relationship, I am not doing anything different. So, mn1 is m1 sin beta and mn2 is equal to m2 sin beta minus theta. Speed of sound is the same irrespective of the velocity component, right. So, this is why I can divide both sides of this also by square root of gamma r t2 and I will get mn2 equal to m2 sin beta minus theta. So, I have all these things. So, I take this, I substitute that here and equate that to here. We finally get, if you equate the two relationship for un1 over un2, I get tan beta divided by tan beta minus theta is equal to gamma plus 1 times m1 square sin square beta divided by 2 plus gamma minus 1 times m1 square sin square beta. And this was pretty much what I wanted, correct. I wanted a relationship which connected m1 with beta and theta, m1 beta and theta with m2 and other downstream properties. So, that is what I have now. So, once you give me one quantity or two quantities in this, I can evaluate all the other things. It is easy to rewrite this slightly. In fact, it is better to rewrite this slightly like this. Just simple rearrangement gives you tan theta equal to 2 cotangent beta times m1 square sin square beta minus 1 divided by m1 square times gamma plus cosine 2 beta plus 2. So, previously in the normal shock wave there was only one quantity given m1, we wanted to calculate m2 and all the other properties. Here there is one more, right, given m1 and either beta or theta, I can calculate all the other quantities. That is what this is telling you. So, given m1 or given any two quantities, here, let me rewrite this, given from the list theta, beta, m1, the other quantity can be calculated from this relationship. And this relationship is known famously as the theta beta m relationship. So, this is known as the what we need to do next is look at this solution and then see what the constraints are for practical application. For example, things like for any Mach number m1, can I deflect the flow through any angle that I want, number one, or for a wave angle, given wave angle and m1, what kind of flow deflection angles are possible? Can I deflect the flow through any angle I want? So, there are many such inferences and questions that we need to look at. Another important question is, this appears to be a nonlinear equation. The trouble with nonlinear equations is they usually have more than one solution. If that is the case, which are the solutions which are meaningful and do not violate second law, and so those are the ones that are going to be seen in real life applications. So, if there is more than one solution which does not violate second law, then which one will we see in an application? That is also important. So, those are the kinds of issues that we need to look at next when we solve this equation and try to obtain solutions and then infer the behavior of this equation. Okay. It is easier not to solve this equation, but to actually look at this equation in a parametric way. So, I keep m1 fixed and I keep, let us say, theta fixed, and then I vary beta, and then I look at the values, the range of values that this takes. So, I can do things like that and then construct curves m equal to constant curves. As the values vary through the other two extremes, I can look at m equal to constant curves and then infer the behavior of the solutions from that, rather than solving for them directly. Remember, that has been our strategy throughout. We want to avoid solving equations. Even when we looked at Rayleigh flow or Fano flow or normal shock wave, we prefer to tabulate rather than solve. That is a much more practical strategy. Here also we will do the same thing. We will not attempt to solve this equation, but we will try to tabulate the solutions or draw curves and then draw inferences from that. Okay. So, inferences from the theta beta m curve is something that we will take up in the next class.